No.
Welcome everybody to the online seminar series, Machine Learning Needs Mathematical Optimization. Today we have the pleasure of having Francisco Jesús Ruiz, who is a research scientist working at DeepMind in the deep learning team. Before joining DeepMind, he was a postdoctoral research scientist in the Department of Computer Science at Columbia University and in the engineering department at the University of Cambridge, where he held a Horizon 2020 Marie Curie postdoctoral fellowship. Prior to that, he completed his PhD and his MSc at the University Carlos III in Madrid. His research focuses on statistical machine learning and in particular Bayesian modeling and inference, which is at the core of this online seminar series. And he has published in leading journals in the field such as Annals of Applied Statistics and Nature, and in leading conferences such as International Conference on Machine Learning and Neural Information Processing Systems. So Francisco, we are very pleased to have you today here. And for the audience, we follow the usual rules. If you have urgent questions, put them in the chat and I will read them to Francisco, and otherwise we will have time at the end for questions. So the floor is yours, Francisco, and thank you again for coming.
Oh, thank you. Thank you. The pleasure is mine. Thank you for the very nice introduction. I was very happy to receive this invitation to speak here today. The talk today is on AlphaTensor. This paper that we published recently on discovering faster matrix multiplication algorithms using reinforcement learning. First of all, this was a joint effort. The paper was published in October, and of course, I'm the one who is presenting here today. But it is a team effort, and here you can see the pictures of all of us. So I will jump straight into the meat. So matrix multiplication. We all know the operation, right? We all learned this operation at high school, and we all learned this kind of algorithm, which is the standard algorithm to multiply two matrices. So for example, in the case of 2x2 matrices, here's the algorithm that we all follow. And I have one question. Can you see the mouse pointer? Because sometimes I refer to some parts of the slide.
Can you? Yeah, we can see the pointer. Yes, we do.
You can see the pointer. Okay, cool.
Yeah.
So here you have the standard algorithm, which it's rewritten in a slightly different way than the one we are used to, but it's the same one as usual. So C11 is A11 times B11 plus A12 times B21 and so on. So I just wrote it in this way so that we can count very easily the number of multiplications. And in 1969, Strassen was trying to prove that you cannot do better than this, that you require at least and at most exactly 8 multiplications to obtain the product of 2x2 matrices. And actually, in the trying to do that, he found out a better way, better in the sense that I will describe next. So essentially, he found that by doing this kind of rearrangement of terms, which is not intuitive at all, he could save one multiplication. So before you had 8 scalar multiplications, now you have 7. So this is perhaps not particularly interesting, except that Strassen's algorithm really shines when you apply it on larger matrices. So if you consider n by n matrices of any size, you can always split them in blocks, like done in this slide, in 2x2 blocks, and then apply the same exact algorithm. So it is still valid. That's the key point. So where the standard algorithm would have 8 multiplications, so 8 matrix multiplication, now Strassen's algorithm, which is the same exact algorithm from a previous slide, except I put everything in capital letters. So now it requires 7 matrix multiplications, and that's where the gain comes from. So by doing that recursively, you get that the complexity to multiply n by n matrices go to n to the power of 2.81, which is already smaller than the n cubed complexity of the naive algorithm. So this was a breakthrough back at the time, and since then, of course, like mathematicians and computer scientists are questioning, like, can we do even better than this? And well, there of course, and there have been many works since then. One result is that if you use a base 2x2 matrix, then you cannot do better than this. This is the optimal thing that you can do. But what if you use a base 3x3 matrix, or 4x4, or in general some kind of some size n by n, right? Like what happens in that case? Can we do better when applied that recursively? Well, it turns out that these are all open problems, and what I'm trying to say here is that even for matrices that are as small as 3x3, we still don't know what's the optimal algorithm to multiply them. There are, of course, some known results, some bounds. So we know that you can do with 23 multiplications instead of the 27 of the naive algorithm. And for 4x4, the only known algorithm uses 49 multiplications, which essentially consists in applying Strassen's algorithm twice. So 7x7 gives you this 49. So you don't obtain any asymptotic gain here. So the reason why we haven't found better solutions yet, better ways to multiply these matrices, is that it's very hard to find such algorithms. So there are many ways in which you can combine the elements of the inputs and output matrix, and so it is a particularly hard problem. So here's where AlphaTensor comes into play. The question that we pose is, can we automate the procedure to find algorithms? And so the main idea of AlphaTensor is, first of all, let's formalize the space of algorithms in such a way that we can do search in that space. Then we express the problem as a game, and then we train a reinforcement learning agent that learns to play that game. So this is more or less the ideas of this work. And these are the main results that we found in the paper. There are many numbers here in this table, so let's go little by little. So the first column here denotes the matrix size. So this is this 2 to 2 represents the product of a 2x2 matrix times another 2x2 matrix. And we know that for that, the best known method is Strassen's method that requires 7 multiplications. So this is the way to read this table. So for example, for 4x4 matrices, the only known method is applying Strassen twice, what we call Strassen squared, and that gives you 49 multiplications. So we do that for many matrices. So we apply AlphaTensor on many matrix sizes. Was that a question, or I heard something?
No, sometimes people hit accidentally. Yeah, they will put it in the chat. Yeah.
No worries. I will ignore them this one. Sorry, I didn't know. So there's at the top we have square matrices like 2x2 by 2x2, but here we have at the bottom rectangular matrices like a 2x2 matrix times a 2x3 matrix. So this is the best number of multiplications required to perform such operation before this work, and this is the results that we achieve using AlphaTensor. So you can see that, for example, for certain matrix sizes, we find more efficient algorithms that reduce the number of multiplications by 1, in this case by 4, which is already one of the contributions of the work. Another contribution is that, well, this is not the results where we improve. Another contribution is that even for those sizes, or the matrix sizes where we match the best known algorithm, we do not only find the previously known result. So this 49, for example, is not just Strassen squared. In fact, AlphaTensor finds literally thousands of known equivalent algorithms that have the same theoretical complexity, but that show that essentially the solution is not unique. There are many ways in which we can perform this operation with the same theoretical complexity, but this leads to algorithms with different properties, and we will expect that later. There's also this column here, which refers to the same problem, matrix multiplication, but in what we call modular arithmetic, that is just operations in the finite field of order 2. So we have binary matrices, and 1 plus 1 equals 0. So if you are in that arithmetic, then it turns out that AlphaTensor finds a better result for a larger set of matrix sizes. And in particular, we improve upon 4x4 and 5x5. And this 47, we were very excited when we obtained this result, because it's the first time since We have a faster algorithm for 4x4 matrix multiplication since Strassen proposed his algorithm in 1969. Of course, this is, I want to emphasize, for the finite field of order 2, so binary matrices. But it might be that that algorithm also exists in the reals, and we don't know. So that's one of the key open questions that we would like to answer next. So just to see how these algorithms look like, here's an example of multiplying a 4x5 matrix times a 5x5 matrix. Here's the algorithm. So this is one of the algorithms found by AlphaTensor. As I said, it's not unique, but it's one of them. Of course, it's very long. Like, the point is not to look through it. So the point is just, first of all, to check that it verified that it has only 76 multiplications, which is what I promised in the table before. And second, to kind of emphasize the point that these algorithms are highly non-trivial. Like, this particular combination of terms is non-intuitive for us at all. Okay, so this is the outline of the presentation. I will first talk about the problem matrix multiplication and tensor decomposition. So why is this called AlphaTensor? Where's the tensor coming from? Then I will formulate this tensor decomposition as a game. Then I will describe AlphaTensor, then some generalizations of it, and then I will conclude. So just to jump into the first point, just like linear operations can be fully represented and fully characterized by a matrix, and this matrix is independent of the inputs and just represents the operation itself. Like, for example, this is a rotation by 45 degrees matrix. By linear operations, like matrix multiplication, is fully represented by a tensor. And again, this tensor is independent of the matrices to be multiplied, and this tensor represents the operation itself. So how do we build this tensor? It's actually very easy. Here's an example for a 2x2 matrices again, because it's easier to visualize. So imagine that we have n equals 2, so n by n matrices. The tensor has size n squared by n squared by n squared, so 4 by 4 by 4. It is this tensor here. And it contains mostly zeros and a few ones. So where the ones are placed, let's look into that. So each slice of the tensor represents an entry of the input matrix A. So you can see entries of the input matrix A, entries of the input matrix B, and entries of the output matrix C. So the ones are placed on those positions that are related. Like, for example, we know that C11 involves A11 times B11, so we placed a 1 there. And C11 also involves A12 times B21, so we placed a 1 there. And by doing that repeatedly, we get that there are n cubed ones. So that's not a coincidence. That's just the number of multiplications that we require. So in this case, 8. So this tensor has n cubed non-zero elements, n cubed ones. So the second point that I want to make here is that an algorithm for multiplying matrices corresponds to a factorization of that tensor that I just described, and that we call the matrix multiplication tensor. So the matrix multiplication tensor can be factorized with rank 1 tensors, as shown here. So it's just a collection of UVW vector triplets. And any factorization of this type represents an algorithm for multiplying matrices. Essentially, I will not go into the details. I mean, I will show an example next, which I think will be clarifying. But the important thing here is that these are the number of terms of the factorization is directly related to the complexity of the algorithm. So if you have more factors, then it's a less efficient algorithm. And if you have fewer factors, then it's more efficient. So to see that, let's revisit Strassen's algorithm through the lens of tensor factorization. So just, I copied again Strassen's algorithm. It's the same one as before that requires 7 multiplications for 2x2 matrices. So let's analyze term by term. So the way to view this algorithm as a tensor decomposition is as follows. So we can see here that we are first reading, in a way, the first and the last entry of input matrix A. So we put a 1 here and here. Similarly, we are reading the first and last elements of input matrix B. So we put a 1 here and here. And then we write the result in the first and last elements of output matrix C. So we put a 1 here and here. So that would be the first term of our factorization. So the second term is just analogous. So the first and last entries of input matrix A, then only the first element of input matrix B. So that's just one non-zero element there. And then you write the result in the two last element of the output matrix, so here and here. There's a sign that is negative there, so you just write a -1. So if you keep doing that for all 7 elements here, so you obtain what is a rank 7 factorization. So this is why a factorization is directly related to an algorithm. So it's kind of equivalent in this sense. Okay, so with that in mind, I want to emphasize the 2 key takeaways of this part, which is that matrix multiplication is fully characterized by a tensor, which is the matrix multiplication tensor, and this tensor is straightforward to form. It's well defined, and that a low rank decomposition of that tensor corresponds to an efficient algorithm for multiplying matrices. So these are the 2 key takeaways. So with that in mind, let's go to formulating tensor decomposition as a game. So we want to do that because then we can apply reinforcement learning on that, which is the thing on which AlphaTensor is built. So how do we define a game for this? So it's actually quite simple. So let's say that at step t, you are giving a tensor st, which initially is just the matrix multiplication tensor, but at later steps of the game, it will be something different. So you're given a tensor, and then your move, so the equivalent of putting a piece on the board, is give a triplet UVW. So you give me this triplet, and then the environment, so the tensor is updated by subtracting the rank 1 tensor determined by the triplet you just proposed. So the tensor, the new state, is just the initial state minus the rank 1 update. So that gives a new tensor that we then compare against the old 0 tensor. So if we reach the old 0 tensor, then we declare the game as finished. If no, then we repeat, and this would be the residual tensor will be your next input tensor for the step t+1. So we keep repeating this until and the goal of the player. So your goal is to reach the old 0 tensor. So every time you propose a move, we give -1 reward. So the reward is just the score of the game. So we have to. So we want. To emphasize, we want to let the agent learn games with high reward. So every time the agent proposes a move, it gets -1 reward. So this is only to encourage games with high reward. So just to recap on this, the game ends at a step t if we reach the all 0 tensor at that step, and the game score is -1 for each step taken during the game. There's also a technical note, which I said that also this could end up in a kind of game that runs forever, and to avoid that, we also have like a maximum length of the game after which we just simply end the game. But anyways, let's focus on successful games. So if you have a successful game, meaning you reach the all 0 tensor at the end, then by construction, the sequence of actions that the player chose, so these UVW triplets, form a valid factorization of the start tensor, of the initial tensor. So this is the equivalent. So a high game score, so a high reward, corresponds to a low rank factorization of the tensor, which in turn corresponds to an efficient matrix multiplication algorithm. So this is the way to map the search for an algorithm into a game. So what we do now is to train a reinforcement learning agent that learns to play this game, which we call tensor game. And that's exactly what we do. So there's one caveat here, you will also a limitation of the whole approach, which is that we constrain the factor entries. So when you propose a move, it's as I said, a triplet UVW. So each element in that triplet is constrained to live in a predefined set. So for example, we typically use this set, integers between -1 and -2 and +2. So why do we do that? First, the reinforcement learning agents that we use require a discrete set of actions. So we want to discretize the search space. Second, we are interested in exact matrix multiplication algorithms. And if we allow for floating point factor entries, then it could happen that we are able to reconstruct the tensor up to some kind of small precision error. And that's not what we want. We want an exact decomposition because that will lead to an exact matrix multiplication algorithm. And the third reason is that most existing efficient algorithms are of this form. This is common practice in the literature, in fact. Of course, that doesn't say anything about the optimal algorithm, but yeah, we just follow this approach. Okay, so we are done, right? Because we recasted the problem of finding an algorithm as a game, and on which we can now apply reinforcement learning. So we are done. Well, not quite. It turns out that this tensor game is quite challenging to solve. The main reason is that if you look at the action space, the size of the action space, compared with, say, board games like Go, it is many orders of magnitude higher. So this is a much more complex game. So the action space is huge. There are other challenges, like for example, we only have one tensor to decompose, which is the matrix multiplication tensor. That's the only thing we care about. So this one instance, it's not enough if we are good at decomposing arbitrary tensors. We want to be good at decomposing this one tensor. We don't have training data, at least in principle, and there are many symmetries of the problem. But actually, both a challenge, but also a blessing that we will exploit later. Okay. So let's go into AlphaTensor now. So this is an overview of the system. So AlphaTensor is a distributed system. By distributed meaning it runs on many computers and many machines at the same time. It is based on sampled AlphaZero, which has been previously successful on board games and yeah, other games in general. It has two components. It has actors and it has a learner. So the learner is responsible for maintaining and training and updating a neural network, and then sends the neural network to the actors, and the actors are responsible for playing games. So that's the kind of overview. So just a little bit more into detail, the learner will take as input a game as an input, and then it has a neural network with two heads, the policy head and the value head. So the value head is the one that is responsible for predicting essentially the rank of that tensor. So in the language of reinforcement learning, it would predict the cumulative reward, so the return. And the policy head is responsible for predicting a distribution over the next action to play. So in the case of tensor game, is the UVW triplet. So given the input gains, the neural network is updated by using quantile regression loss for the value head and a standard cross entropy loss for the policy head. And then once it updates the network, learner sends these network parameters, this updated model to the actors, which are responsible for playing games. So the actors receive the neural network parameters, and then they play the game by simulating trajectories using Monte Carlo tree search, MCTS. So we're not going to the details of MCTS, but essentially it's like the planning mechanism of the actors. And the main goal why the actors are doing this is to find and to improve upon the current policy dictated by the neural network. So the neural network tells you a distribution over the next action to play, but the actors say, okay, I don't really trust this neural network, so I will improve upon it using MCTS. So using this, it produces a sequence of moves which do not follow the neural network policy head distribution, and then they send this game to the learner, which again responsible for updating the neural network parameters to match these improved moves that the actors were playing. So essentially, you can see the actors as being responsible for generating data. Okay, so you can see in this picture that there is some addition.
Sorry, yes. There is a question. So it says here, if the action space is so huge, how is the neural network able to return a distribution over actions?
Yes, that's a really good question. Yeah, of course, you cannot enumerate all of them. So what we do is to use an autoregressive policy head that essentially produces say the vector u first, then v conditioned on u, and then w conditioned on the previous two. So for each of these intermediate steps, you can evaluate probabilities, which means that you can, by the chain rule, you can evaluate probabilities of the whole thing. But yeah, I mean, this is just one way that we found to do that. It doesn't mean that it's like the best way, but there might be better ways. But that's how we do that at the moment.
Thank you.
Yeah. Okay. So that's a good point. Another point related to that question, which is if we have so many possible actions, we cannot enumerate them. And then at MCTS, you would have to enumerate them. But that's why I said at the beginning that we use sampled AlphaZero, which means essentially we just sample a few candidate actions because we cannot enumerate them all. Okay. So in this diagram that I've been following, there are a few ingredients that are specific for AlphaTensor as opposed to other applications of AlphaZero. One of them is that, as you can see here, there are two sources of inputs, two sources of data. One is the played game by the actors, of course, but when we also use some set of pre-generated synthetic demonstrations, so synthetic data. What do we mean by that? So the problem of factorizing a tensor is hard. In fact, it's NP hard. But the other way around, so if I know the factors, reconstructing the tensor is straightforward. So this direction is hard, this direction is easy. So taking that into account, we pre-generate lots of synthetic data, so tensor factorization pairs, by just randomly sampling factors and then aggregating them together to give us tensors. So that's a very cheap way to produce training data. Perhaps, arguably, one problem with that is that, or one difficulty is that the data that we generate this way, the tensors that we generate in this way, essentially randomly, might be very different from the tensor that we care about, which is the matrix multiplication tensor. So, I mean, that is true. That brings us to the second ingredient of AlphaTensor, which is diversify the target. So it turns out that this target, the matrix multiplication tensor, was, as any tensor, can be represented in many equivalent ways using change of basis. So a change of basis is just like applying multiplying but an invertible matrix. Each of the modes, it pair of modes of the tensor. Because it is invertible, you can recover back. You can go back from any base. You can go back to the original standard base. So by doing that, we hope to have more diversity. And we do that, this random change of basis, we apply that at acting time. So when the actor takes a tensor, the first thing the actor does is apply a change of basis out of many, and then plays the game in the change basis. So it plays the game the starting tensor is not the standard matrix multiplication tensor, is the matrix multiplication tensor after change of basis. So it has some advantages to do that. First of all, diversity. I already mentioned this. This provides a natural exploration mechanism. Second, it suffices to succeed in one base, because if you think about it, like producing many different random change of bases, if you find a low rank decomposition of any of them, then it's you can always invert and convert back to the original base, and then you also have a low rank decomposition in the original base. So that is another advantage. The third advantage is a little bit less straightforward, so enlarges coverage of the algorithm space. So if you remember earlier, I said that the factor entries are constrained to be in some set, essentially between -2 and +2. But that's true. That applies in the actions that the actor is following. So in this particular base, when you convert back to the standard basis, you also convert the actions back to the standard base, and it might happen that after doing that, the factors actually have entries that are outside of this range. And in fact, that we observe that actually happens. Okay, so I will go to the third ingredient of AlphaTensor, which is this what we call generalist agent. So if you recall the table of results that I showed at the beginning, we have many matrix sizes, right? So perhaps the simplest approach, or the most standard one, which is also the one that we tried first, is to train one agent for each target size. So for 3x3 matrices, we train one agent. For 4x4, we train another agent, and so on. But it turns out that it was much, much better to have one single agent that is trained on all matrix sizes at once, or all matrix sizes that we consider, so all the ones from the table. It might not seem intuitive, but actually what happens is that there is a transfer of knowledge across sizes. So the agent is learning to use perhaps some information from smaller tensors into larger ones. So that helps a lot. So where do we do that step? We also do that step at the beginning of acting. So the actor chooses one of the tensors to play, so one of the sizes, and then applies the change of basis. So besides obtaining better performance, this scheme is also more efficient because we only need one single experiment to find the result from the table. We don't need to run some number of experiments in parallel. So the fourth component of AlphaTensor, compared to, again, AlphaZero, is the architecture, the neural network architecture. We leverage the power of transformers. We use like a sequence of attention operations, and they are designed in such a way to kind of exploit the information that the inputs are tensors. So we do attention over slices of that tensor that are related. Essentially, that's the high-level idea. Again, I will not go into the details of the architecture, but I'm happy to take questions about that. So here's another ingredient, which is exploiting symmetries. It turns out that this problem has many symmetries that can help us reduce the action space. So for example, consider these two actions that I have here in green and orange. There are different actions that are different triplet UVW, but I have multiplied by -1 some of two of the vectors. So you can see the differences here. So this V is now -V, this W is now -W. But of course, both actions correspond to the same exact rank 1 tensor, right? So that's true for any choice of lambda 1, lambda 2, lambda 3 that multiplies up to 1. So to kind of remove this symmetry, we define something that is called the canonicalized form of a triplet. The canonicalized form of a triplet is just defined in a way such that the first non-zero element of both U and V is positive. So you can this would be the canonicalized form of these two actions. So when we do that, we always we define that, and we always show actions to the agent in canonical form, and hope that the policy head will learn to imitate that, and therefore reduce in a soft way the action space. There are more symmetries on the problem. Like, for example, actions are commutative, right? Because the underlying operation is addition. So you can two actions played in different order are pretty much equivalent. So we use that fact to kind of devise a data augmentation technique. So for every played game, we randomly select one action and swap it with another one. And by doing that, we get one new data point, one new game for free, essentially. So for every played game, we store in this database of game, we store the played game and also the permuted version of it. There are many other ingredients that I don't have time to cover today, like saying permutations and new components in the policy target and acting, but I will not go into that today. So instead, I will focus on the results. This is the table again that I showed at the beginning. First of all, I would like to mention that we using these improved factorizations and the fact that we have hundreds or potentially thousands of non-equivalent factorizations for each size, we're able to combine in a yeah, in a way that I will not describe either, but you can find the details in the paper. But you can combine these results to improve upon the rank of larger matrix multiplication tensors. Like for example, in this plot here, we have on the x-axis the best rank known before this work, and on the y-axis the improvement in rank. So you can see, like for example, for 9 multiplying well 9 by 11 times 11 by 11 matrix, we improve the rank by approximately 30. Just this is obtained just by combining the results that we find, yeah, and leveraging the fact that we have many non-equivalent factorizations for each size. Also, we were, as I said at the beginning, we were very excited about this 43.7 here because it leads to an asymptotic complexity of 2.77. So just to understand this number in perspective, let's revisit the history of matrix multiplication algorithms. So we have here a plot, like this is kind of a cartoonish version of it, where on the y-axis we have the complexity exponent, so something between n squared and n cubed. And on the x-axis, we have the size of the base matrix. So algorithms with better complexity are more towards the bottom of the slide because they have lower exponent. And more practical algorithms are towards the left because they can be applied recursively. So this is where Strassen sits. It has a n to the power of 2.81 complexity, and the size of the base matrix is 2. There have been many other works. Of course, this is not exhaustive. And there, the kind of record on the exponent on matrix multiplication is the order of 2.37. In fact, this I think. No, this is updated. Yes, sorry. So yes, so you can see that that these matrices here, like they have astronomical sizes, so that's why they are not practical. These matrices don't fit into memory, but it's still very interesting to study what is the asymptotic complexity of this of the matrix multiplication operation. So essentially, we ask the question: is there something that is practical and fast? So this is where this result that I mentioned earlier sits. So this is for 4x4 matrices. We get 2 to the 2.78. Yeah, so that's why we were excited about this result. But I would like to mention that this again, I want to emphasize that this is on binary matrices on a finite field. Still remains open the question of whether this algorithm also exists in the reals. So I also want to mention this, which we were very excited that after the publication of the paper, actually two researchers, Cowers and Musbauer, published a follow-up paper where they improved upon some of the algorithms found by AlphaTensor, and then there was like many articles on the press talking about the competition. But actually, we like to think of this as a kind of collaborative approach. We know that the results of AlphaTensor are by no means optimal, but we hope that they're useful for the community to improve upon them, or maybe to devise, find some patterns across those algorithms that maybe lead to some new discoveries. So I think that there's a nice summary in a recent Quantum Magazine article that we think explains the story really nicely, and we believe. So I don't have a lot of time left, but I would like to talk about generalizations of this AlphaTensor approach. So as I said at the beginning, like AlphaTensor is a reinforcement learning agent based on AlphaZero that is good at the tensor game. Tensor game is about decomposing tensors. And I said at the beginning also that matrix multiplication is one instance of a bilinear operation. But there are other bilinear operations that are not exactly matrix multiplication that we can also recast as a game in exactly the same way and apply AlphaTensor. So we did that on a few examples. So here is the example of multiplying a skew-symmetric matrix times a vector. So it's a particular constraint. So assume a particular kind of structure of the matrix. It's skew-symmetric or anti-symmetric. And then it turns out that when we applied AlphaTensor, it discovered algorithms that look like this when you plot them. So these are the UVW elements plotted for n equals 3, n equals 4, n equals 5, n equals 6. And you can see that there's some kind of pattern. So it turns out that this pattern generalizes to any other size. And we were able to prove that. And that reduced the complexity of skew symmetric from n squared to 1/2. So it's the same order of n squared, but we reduce the complexity of the constant in front of it. And combined with our previous paper, it turns out that we found the optimal algorithm, because this is also so this is also a bound, so it cannot be improved. So this is another example of the generalization of AlphaTensor, where we applied to rediscover the discrete Fourier transform. So we do that by considering the bilinear operation of a circular convolution of two vectors in a finite field of order 17 in this case. And when we apply that, it turns out that AlphaTensor for some sizes, and it was 2, 4, 8, it finds some components, some U, V, and W vectors, which are essentially the discrete Fourier transform and the inverse discrete Fourier transform matrices. So that is not surprising. Well, I mean, that is not surprising. I mean, it is surprising that it find it. It is not surprising because we know that this is the optimal solution, and this is the optimal solution for this problem. So when you want to compute a convolution, the best thing to do is to compute the DFT of both inputs, then multiply in the Fourier space, and then compute the inverse Fourier transform. So that's essentially the algorithm that AlphaTensor finds. So there are many other ways in which AlphaTensor generalizes. One of them is practical runtime. So here, what we do is we were thinking, okay, so we find many non-equivalent algorithms. So is there a way to steer AlphaTensor toward finding algorithms that satisfy some property? And in this case, that property is the actual running time of the algorithm when you execute it on a specific hardware platform. So far, up to this point of the presentation, I've been considering asymptotic, so the theoretical runtime. But in practice, things are different. Of course, like an algorithm that is optimal and is not necessarily faster when you run it on a GPU or on a TPU. So here, that's what we do is to say, okay, let's try to find an algorithm that is specifically good at a given hardware platform, say GPU, for example. And here we find algorithms that outperform outperform upon Strassen squared. And you can see, for example, in this plot for different matrix sizes, the speed up that they give on an NVIDIA GPU, and we have similar plots for TPU and so on. So this is possible because AlphaTensor does not require any specific properties for the reward that we specify. So the reward can be any signal that's not be differentiable or anything like that. So in this case, the reward that we use is something that includes a term that is measures the actual runtime of the algorithm that is just proposed. Another way in which this can be generalized is what is known as border rank. So border rank is this notion of rank of a tensor, but that it contains some kind of symbolic coefficients in the factorizations of UVW, some epsilons. And then you recover, when you multiply UVW together and add the triplets, you recover something that is equal to the target tensor up to order of epsilon. So if you make epsilon small, then you would have something like an approximate matrix multiplication tensor. Or an approximate decomposition. Sorry, an approximate decomposition of the tensor. So this is also interesting, this problem in the mathematical community, and in particular for the problem of matrix multiplication as well. And so we ran just as an use case to showcase this in a small experiment. We ran this on a specific tensor, and we find, using AlphaTensor, we find also border rank decompositions. And again, this is possible because we can use any arbitrary reward. Okay, so I think I'm running out of time, and I'm also I'm reaching out the end of the presentation, which is good, I guess. So just to conclude, AlphaTensor transforms. The idea of AlphaTensor is to transform a math problem, or algorithmic problem in this case, into a game, and then develop a neural agent that learns to play that game. To do that, we use a problem-specific knowledge. In this case, like we exploit many things like symmetries of the problems, like the fact that we're decomposing tensors, so we can use generate data for it. I showed, or I hope to have showed today, that AlphaTensor is flexible. It supports different rewards and customizable. It also supports different factor entries. It has also some limitations, which I have mentioned. One of them, perhaps the main one, maybe, is that you have to predefine these factor entries. And the second one, another limitation, is that there's no optimal liquidity guarantee. So you run AlphaTensor and you find the composition and that of a given rank, and that doesn't mean that's optimal. So we don't know whether you can improve upon that or not. So yeah, I think this is good to keep that in mind. So in terms of future work, we have here some ideas. Like, for example, you could use the fact that you can define any arbitrary reward to optimize other metrics, such as numerical stability, which is something I didn't mention at all in the presentation, energy usage, or things like that. Or even other notions of rank, like Euler rank, or even other settings, like, for example, applying this for non-negative matrix factorization. So I just want to conclude here with this sentence that AlphaTensor goes beyond human intuition to find efficient matrix multiplication algorithms. And we have found this improvement upon Strassen square method on 4x4 matrix multiplication in a finite field. And again, I like to emphasize the fact that it finds thousands of efficient algorithms for efficient algorithms for each matrix size, not just ones, which also shows that the space of algorithms is richer than we originally thought. So with that, I would like to conclude. Thank you everyone for listening, and I will be happy to take any questions now.
Yes, thank you so much for your very impressive presentation. We have a question from Emmanuel Ponce, and I believe that you have now the rights, Emmanuel, to
yes,
unmute.
Thank you, Dolores.
Okay.
Thank you much for your interesting and impressive presentation, Francisco. I have one comment and one question. The comment is very well related to your last slide. It may pay for you to have a look at what is called CP rank, which is dealing with symmetric non-negative matrix factorizations. And you ask for the minimal number of columns in such a factor, right? It's not the rank. It can exceed the rank. It can be, it increases actually quadratic with the order. But there are a couple of cases where it's unknown what the maximal CP rank is. Maximum possible CP rank for a given, say, 6x6 matrix is unknown. They are just bounds, which are shown to be asymptotically tight. So I think AlphaTensor could shed more light on this. But this is, for my own curiosity, I would like to ask a question whether I understood it correctly. So you were mentioning this green TauN or TN, which you feed instead of sampling across a huge variety of possible starting points. Let's put it like this. Was it always the best known algorithm which you encoded for this TauN, or was it something else? Did you use prior knowledge for it?
No,
the best knowledge?
No. So this we didn't. So this TN is the tensor. So essentially, you build it by using. So essentially, like using the properties of the matrix multiplication. So when I explain here in this slide how to build this tensor.
Yes.
So we just do, essentially we're using the knowledge, if you want, of the naive matrix multiplication.
Of matrix multiplication structure. So what could also be used is a known factorization, a known, right?
This is a really good point.
Never learned this.
This is a really good point. We could,
Or would this distract the neural network?
Yes, so we could use these known factorizations in the here. So essentially include them in the data, right? As part of the data. This is a really good point, and we didn't do that, but yes, we could do that, and it might help. Yes.
And a related question, of course, I was curious, did you monitor the rank across the iterations?
Yeah, of course, yes.
And is it always decreasing?
Not always.
Not always.
Generally, yes. Okay. Generally, yes, but it might happen that, and that happens sometimes, that the network plays a very good game, say, manages to decompose the rank, but then, yeah, of course, that game is stored in the database, but then the neural network is not able, for some reason, well, I mean, it's only one data point, right? So the neural network doesn't pick up on that, or doesn't update in the right direction. I mean, it is updated in the right direction, but there's so many data points there that maybe that one data point doesn't have enough weight. And then when you play a future game on the same tensor, it might not find the same result. So it does happen, yes. It's not generally the case. So the trend overall is increasing. But it happens.
Increasing
it can happen, yes.
Yeah. Thank you very much.
Exactly. So,
thank you.
Yeah, thank you.
Congratulations once more. Thank you.
Yeah, thank you. Thank you.
Thank you, Emmanuel. Jason, can you give the microphone rights to Alberto? He has a question, or two questions, I think. Alberto, are you?
Maybe can you hear me now?
Yes, we can hear you now.
Okay, so it's just what I wrote on the chat. First of all, thank you for the presentation. I found this really amazing. And my question was that I understand that the optimal policies are the different factorization or algorithms, right? The policies you want to find.
The policy head, yes, exactly. So the policy head, yeah, exactly. The policy is a factor triplet. Yeah.
Okay. So, and you've commented also that there might be 1,000 or maybe, I don't know, maybe infinite ways of factorizing this. So my question is there is any way to give a bound on how many there will be?
Oh, I see. This is a good question. To be honest, I'm not sure about that. So the question is a bound on how many factorization of a specific rank there are.
Yeah.
Yeah, I'm not sure about that. Yeah, sorry.
Oh no, so I had a comment that it is clear that, and you've also said that we're losing explainability with respect to the basic algorithms, right? So I just wrote that this is going to be difficult to explain to young students at school.
Yeah, I mean, to be honest, like even Strassen's algorithm, I am unable to find any intuition there personally. Maybe there is. Yeah. So yes, I mean, you're right. You're right. Like I'm. So the nice thing about this approach is that it discovers a provable correct algorithm. So here, once you discover the algorithm, you have it there, right? Like you just can use it anytime. So the algorithm, you can analyze it, but but that's it. That's about it. So how it came up with the algorithm in the first place, it's of course that's up to the neural network and all this kind of procedure that we follow the AlphaZero setting. But yes, you're absolutely right. It's really hard to draw any intuition from the algorithms that it finds because it's just like a non-intuitive combination of terms.
Yeah, thank you so much.
Yeah, thank you.
Thank you. So are there any other questions from the audience? Well, if not, thank you very much again for coming to the online seminar series and to present.
Thank you again for the invitation.
very novel research of you and your team. And to the rest of the people, we see you next week again with another seminar. Thank you, everybody.
Thank you.
Thank you.
Thank you.